Hello and welcome. In this video, we will talk about logic. So, we'll be covering what is logic, what are the different connectives that are used to extend the concept of logic. We will also discuss what is tautology, what is contradiction, and how to prove them. Logic is a way to quantitatively develop a reasoning process that can be replicated and manipulated with mathematical proofs. That means we are given some statement, and through the sequence of steps, we will prove that statement. That is known as a logic. Okay, we will apply some appropriate rules, some simplifications, and we will say that okay, whatever statement is given is true. So we are proving the validity of the statement through logic. It is the ability of humans to reasonably think about something with the help of proper proofs and inferences. Proposition is a declarative statement having value true or false. So proposition is always a statement with fixed value. Either it's true or it's false. If you cannot infer the value truth or false from the statement, then it is not a proposition. Like man is mortal. So that's obviously true. So that's the proposition. Sun rises in the east. That's true. So it's a proposition. For any value of x for x greater than 2 power x. It's obviously true, so it's a proposition. Answer of proposition depends on value of certain variables. Such variables are called free variables. Let us take the equation x square minus 2xy plus 3y square is equal to 16. So the statement will be true, but for specific set of x and y, so the validity of this statement depends on value of x and y. So x and y are called free variables. Connectives. Connectives are a kind of operators that will connect different simple propositions, and it will make compound proposition from that. So we are given a simple statement. We can use different connectives to connect them. Like in English, we have a and, but, or, right? So similarly, we have some such connectives to connect the propositions. If P and Q are two propositions on the same universe, then they can be combined using 5 different ways. One is disjunction, so it is same as a union. Conjunction, that is same as an intersection. Negation, that is complement. Implication, so that is if-then rules. And equivalence, that is if P implies Q, then Q implies P kind of statement. Let us try to understand what happens in each of these connectives. So disjunction, so if at least one proposition is true, then the compound proposition will be true. So now we have connected P and Q through disjunction, and the truth value of that compound statement depends on truth value of the individual propositions we have used, right? So if any one proposition is true, either P or Q, then the entire compound proposition P union Q or P disjunction Q would be true. So it is basically performing logical OR operation. So we can say that a truth value of P disjunction Q is same as max of truth value of P or truth value of Q. So truth value of P could be 0 or 1. Similarly, truth value of Q could be 0 or 1. So any one of this is true, then the output or the compound proposition will have the truth value true. So this is the truth table for the disjunction. It is same as the OR gate. Right? P can be 0, 0, 1, 1. Q could be 0, 1, 0, 1. So we have 4 combinations as we have 2 propositions. And their disjunction would take value 0, 1, 1, 1. As you can see that the P union Q would take the maximum value of truth value of P or Q. In first row both are 0, so it's 0. In second to fourth row at least one is 1, and that is the maximum value, and that is returned as the output or the truth value of P disjunction Q. Conjunction is same like intersection. The truth value of the compound proposition is true only if both statements or both individual propositions are true. If both the proposition P and Q are true, then the compound proposition will be true, and it basically performs logical AND operation. Okay? And mathematically we can define the truth value of compound proposition P conjunction Q as minimum of truth value of P or truth value of Q. So its truth table would look like identical to the truth table of AND gate. That is, when both propositions are true, then only it will take value 1, otherwise it will be 0, because 0 would be the minimum value in 3 rows. The negation of a proposition P is false when P is true and vice versa. So if truth value of P is 1, then truth value of negation P would be 0. And if truth value of P is 0, then truth value of negation P would be 1. So this is how we can represent the truth table. And that negation proposition is represented by either tilt P or bar P or P complement or P dash, something like that. And from this, we can also derive the law of De Morgan. That is, negation of P disjunction Q is same as negation P conjunction negation Q. And the another law says negation of P conjunction Q is same as negation P disjunction negation Q. So it's the same as a set, right? Negation, or we can say P union U complement is same as P complement intersection Q complement, and vice versa. Implication, that is P implies Q. It is also read out as a P entails Q, and it is also written as if P then Q, and where P is called the premise of the statement or the hypothesis of the statement, and Q is called the conclusion. For example, if our statement is like that, if you score 90% or above in this subject, then you will get A grade. So the value of conclusion depends on the premise. So the first part, if part, is called P, and the later part, that is you will get A grade, it will form the Q of the statement. So we can represent such rules in P entails Q format, and P entails Q is equivalent to not P disjunction Q, and truth value of P implies Q we can compute in the same way. We will take the truth value of not P union Q. This is very popular formula. You should remember, we are going to use it at many places. And in another way, we can say that P implies Q will take value 1 if truth value of P is less than or equal to truth value of Q, and it would be 0 otherwise. So whenever truth value of Q is greater than truth value of P, it will be 0, else it will be 1. And this is the truth value. If P is 0, Q is 0, then P entails Q would be 1. P is 0, Q is 1, truth value of P entails Q is 1. When premise is true and conclusion is false, then the truth value of P implies Q would be 0, otherwise it is 1. Because P entails Q says that whenever our premise is true, conclusion must be true. If premise itself is false, we are not worried about the conclusion, right? So even if P is 0, whatever may be the value of Q, P entails Q will remain 1. But Q must be true when P is 1. So if P is 1 and Q is not true, then the truth value of P entails Q should be 0. Okay? So this is how the table is formulated. The equivalence connective is generally used when we have a dual implication. In previous slide, we have seen one-sided implication from P to Q, but whenever it is true in both the direction, then we can use the equivalence. That is, if P entails Q and Q entails P, then we can say that P equivalence Q. And the truth value of P entails Q would be 1 if the truth value of individual propositions are same, and it would be 0 if they are not identical. So even both propositions P and Q are false, then the truth value of P equivalence Q would be true. And if both are 1, then also truth value of P equivalence Q would be 1. As shown here, the first row and last row have value 1 because the truth value of P and Q are same in them. Whereas in row number 2 and 3, they are different, and hence the P equivalence Q doesn't hold. Let us try to prove P equivalence Q first. So it says that P equivalence Q is same as P entails Q conjunction Q entails P. And we already know that P entails Q we can always write as a not P union Q. So let us first compute not P. So the truth value of P is true, true, false, false. So not P would be false, false, true, true. And as we know, P entails Q is same as not P union Q. So we'll take the union of second and third row, that is negation P and Q. So that will result into T, F, T, T. To compute Q implies Q, first we'll compute, so that will be equivalent to negation Q union P. So we'll compute negation Q, that is FTFT. Take the union of this column with P, so that will give us TTFT. And then we have to take intersection of both P entails Q and Q entails P. We'll take the conjunction of that, and that will give us TFFT. So as you can see that wherever truth value of P and Q are identical, the equivalence has a value true, and in rest of the two cases it is false, and hence it is proved that whatever we have claimed is actually correct. Summary of the connectives, that we have two connectives and we have two propositions P and Q. It could be more, it could be generalized to n number of propositions, but for 2 there will be 4 rows in the table. If there are 3 propositions, there will be 8 rows. For 4 propositions, there will be 16 rows. So in general, if we have n propositions, then the table, truth table, will have 2 power n rows. Right? So disjunction says that if x belongs to A or x belongs to B, and hence T of P disjunction Q would be max of this T of P or T of Q. Conjunction says that it should be minimum of T of P and T of Q. Negation says that it should be just complemented. Implication means whenever the proposition premise part is true, then conclusion must be true. If conclusion is false, in that case the truth value of P entails Q would be false. In rest of all the cases it would be true. And equivalence says that whenever truth value of both propositions are same, then it would be 1, otherwise it would be false. So this is the summary of all 5 connectives used to create compound propositions from the simple proposition or from the atomic propositions. Tautology. So tautology is a compound proposition which is always true irrespective of the truth value of individual simple propositions. So suppose I have proposition P and proposition Q, and I have some compound proposition created out of that. So if P and Q value of P and Q is 0, 0, 0, 1, 1, 0 or 1, 1, all 4 possibilities. For any of these inputs, if my compound proposition is 1 for any random input, then I can say that it's a tautology. Tautologies are useful for deductive reasoning, for proving theorems, and for making the deductive inferences. Right? So when we are trying to simplify something, or when we are going to infer something, reason something, in that case tautology will greatly simplify our computation. And such 2 very popular laws or tautologies are P conjunction, P entails Q will lead to Q, and Q complement or Q negation conjunction with P entails Q would give you the P bar. So remember these 2 rules, they are going to useful in future. Let us try to prove that P union negation P or P disjunction negation P is a tautology. So in first column we have P, in second column we have a negation of that, and in third column we have union or the disjunction of both the proposition, and that leads to TT. So you see that whatever may be the value of P or negation P, their compound proposition is always true, and hence this statement is called as a tautology. Show that P entails Q union Q entails P is a tautology. So we have 2 propositions, so there will be 4 rows and 4 different input combinations: true, 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 false, false, true, false, false. First we'll compute P union P entails Q, then we'll compute Q entails P, and then we'll take the union of that. So P entails Q is given by negation P union Q, fine. Or we now already know that P entails Q would be true in all the cases except when premise is true and conclusion is false. So that is happening in row number 2. So row number 2 have value false, and rest of all would be true for P entails Q. And in Q entails P, when Q is true and P is false, in that case only Q entails P would be false. In rest of the cases it would be true. And if we take union of these 2, then it is T, 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 T. So you see that whatever may be the combination of P and Q, this given statement is always true, and hence we can say that yes, it is tautology. Check if P disjunction P entails Q is tautology or not. So let us first compute P entails Q, and P entails Q, we know that it is given by negation P union Q. So first we are computing negation P, then we'll take the union of that with Q, so that is TFTT, and again we'll take the union of that with P to compute the P disjunction P entails Q. which is T, and hence we can say that given statement or given compound proposition is a tautology. Contradiction is exactly inverse. It is a proposition that is always false regardless of the truth value of individual simple propositions constituting that compound proposition. So we have two propositions, and if we put the truth value of those propositions, and then when we evaluate the compound proposition, it is always going to be false for any inputs or any truth value of constituent propositions. For example, A intersection A complement is phi. Okay? So that we know that it is law of contradiction for the sets, which is always going to be phi, or A intersection phi is always remaining phi. So this is a contradiction that will never have any value. It is always false. Such one popular contradiction is P conjunction. Negation P is false. That's very obvious, right? That we can easily prove that the first column is having truth values true and false. Its negation would be false and true. And when we take conjunction of the truth values of both, it is FF. Okay? So in case of tautology, it would be TT. In case of contradiction, it would be FF. So given statement is contradiction. Prove that P equivalence Q conjunction P bar conjunction Q is contradiction. So you might be asked this kind of questions in competitive examinations. Some statement is given and you have to check whether it is a tautology or not, or whether it is a contradiction or not. So let us start with this. Negation P or not P would be FFTT. P equivalence Q, we know that when P and Q both are same, then its truth value will be true, otherwise it will be false. So for first and last row, it is true because in first row, P and Q both are true, and last row both are both are false. And in rest of the two rows, one is true, one is false, and hence this is the truth value of P equivalence Q. Let us take the conjunction of that with P bar. So that will be FFTF. Fine. Because in last row only, P bar and P equivalence Q has value true. In other three rows, it is either one of them is false, and hence the conjunction would be false. And then we have to take conjunction of that with Q. So this is the entire statement. And as you can see that for any value of P and Q, the given statement is remaining false every time. And hence this statement is contradiction. Thank you. That's it for today, folks. See you in next video. If you think this video was useful to you, then please like, comment and share. Don't forget to subscribe the channel CodeCrucks. Press the bell icon for the notification of latest videos. Stay connected, stay tuned. Thanks for watching. Bye-bye.